Hello everyone, Mr. John here with this week's Thursday Tidbit, where we're going to be talking about Euler's Theorem today. Now, this is an extension of a previous video we did, so you can check that one out as well if you want a little bit of review of Euler's Totient function. But we'll talk about it quick and what we need to know today here at the beginning of this video too. Euler's totient function, also called Euler's Phi function because of the notation, is defined so that it's equal to the number of integers from 1 to n, or sometimes from 1 to n minus 1, that are relatively prime to n. Right? Of course, n is never relatively prime with itself, so you could define it either way you want there, but I like it with this symmetry we have in that case. As our simple examples, any number less than a prime, so 1, 2, 3, up to any prime number, one less than that prime number, for example, these are all relatively prime with p. So if we have a prime number, then we have p minus 1 numbers, all of the smaller ones, so phi of p is p minus 1. One of the common ones we'll look at today, and you'll see why it's important in a second, or extensions of it are important. Phi of 10 is 4. Remember, as of now, we just want to list out those numbers. So the relatively prime numbers to 10 are 1, 3, 7, and 9. Those are all relatively prime to 10, and that would give us why phi of 10 is 4. Now, there are times you want to list these numbers. We explored that more in that other video. Of course, today we're more interested in this as a function. And luckily, there's a pretty nice formula that we have for phi of n as well. So let's review that as well. Remember, this depends on the prime factorization. So if you have all of these different primes, p1 to the e1, p2 to the e2, etc. in this case, up to pk to the ek there, we can actually calculate this number dependent on each of the primes in the prime factorization. So again, for each of those primes, we start with the number n. So let me highlight that at the beginning. But then you take that first prime, subtract 1 from it, and divide it by p. So you can think of these as fractions. We have p minus 1 over p, then we have p2 minus 1 over p2. And this continues all the way down to pk minus 1 over pk. So we have this for each of our primes. This gives us our formula for phi of n there. So we wanted to double check our examples from before. Well, this is pretty simple for a prime number. But for example, what if we had that phi of 10 example again? So phi of 10 would be the number 10. 10 is, of course, 2 times 5. And so we can multiply this by a half and then 4/5. So remember, we have a 4/5 here. And so then the 10s cancel, and we are left with 4. But we'll see, and this one will be the most important one we look at today, is this also extends, and it is important to remember that we just need to know the primes there. So 2 squared, 5 squared, we actually don't care about the squared portion. We still have our number times a half times 4/5, and it's pretty easy to see then this is going to be 40. So we have pretty nice relationships. 4, 40. If you did 5, 1,000, it would be 400. But just knowing the prime factorizations, we can calculate these for all of the different powers of 10 as well. Now, where is this formula and function going to be useful? That's our main topic of today with Euler's theorem. So let's take a look at Euler's theorem then. So if we have a relatively prime number, so we have two numbers a and m. M is going to be our modulus. This is going to be our mod. This is what we're going to be dividing by and taking the remainder of. So if we have a relatively prime number, then a raised to the phi of m. So I just want to point out here that that is where our phi of m is showing up. This is going to be equivalent to 1 mod m. Now, just as a quick reminder of our modular arithmetic stuff, this tells us, in other words, a to the phi of m. When we divide that thing by m, we have remainder of 1. So this is really talking about a remainder problem, and that is our review of that if we are a little bit unsure of that modular arithmetic notation. But we're going to be doing that a bunch today. Just remember, it's always talking about remainders. So anytime you have that notation, we have, just think about remainders in that case. Now, this is the main theorem. If you're just worried about the theorem, we're not going to do the full proofs or anything there, but it's a little bit unfair to not mention Fermat's little theorem, as it's called. This is only for a prime number. So if p is a prime number and if a is not a multiple of p, so again, this is another way of saying for a prime number, a and p are relatively prime. So we have a very similar setup. Then a to the p minus 1 is equivalent to 1 mod p. Now, I want to note and remind us, remember, what did we calculate for phi of p? Remember, phi of p itself was p minus 1. So in fact, this Fermat's little theorem is implied by Euler's theorem in this case. So if you have Euler's theorem for free, in a sense, you get Fermat's little theorem in this case. Now, why do we still mention both? Well, Fermat's little theorem came up first in history. Fermat came up with that. He didn't at least publish a proof. Euler published a proof, then extended it to give us Euler's theorem there. And really, if you want to understand the proofs of these, you really should start with Fermat's little theorem. If you understand the proof of Fermat's little theorem, there's some nice relationships with mods. It's a good way to practice some of your modular arithmetic facts and tools. Then you basically have the idea of Euler's theorem as well. So these are really intertwined in terms of both their history, but really if you're learning about these and want to learn about the theorem, you should also start with Fermat's little theorem there. But as far as applications are concerned, Euler's theorem is quote-unquote stronger. If you have Euler's theorem, then that gives you as a corollary Fermat's little theorem as a basic result, because we know phi of p for a prime is p minus 1. So that, as far as theory is concerned, is all you need. Okay, let's see how this is helpful in practice. And there's lots of different applications of this, but I want to stress that we have a lot of fancy symbols on this screen and stuff. This can still be helpful in problems that don't seem like they require or should require that much fancy theorems as well. And the best example of that is the last digits, or last 2 digits. If we're doing modular arithmetic, remainders, we're used to finding patterns. Remember, you can always find patterns. That will come up in just a second here as well. But what are the last 2 digits of 353 raised to the 3005th power? Of course, you don't want to actually calculate this, and we want to be thinking here, well, what does last 2 digits mean? Well, remember, last 2 digits, this is basically telling us that we want to work mod 100. So if we have the last 2 digits, we don't care about any place value 100 and above, so we can calculate everything mod 100 in this case. So right off the bat, we don't care about the 3 in front. right? If we only care about the last two digits, this will be a common theme in a bunch of these ideas and stuff. We can just write this right off the bat as 53 raised to the 3005th power. Now, let's do some work off to the side here as well. Asking a question, is 53 relatively prime with 100? Well, yep, that is. So GCD of 53 and 100 is 1. Now, you don't need to necessarily write this out if you're showing the work, but I just want to stress that that is what we need for Euler's theorem, or Euler's extension to Fermat's little theorem. Because this tells us that 53 raised to the phi of 100, which, don't forget, we already calculated that. That was 40. This tells us that we have 53 raised to the 40th power is equivalent to 1 mod 100. And right, the mod 100 part, I'll keep writing down, but just remember everything we do is pretty much mod 100. So for example, right, officially speaking, I should have mod 100 right here as well. But if you're just doing scratch work and things like that, you probably will not necessarily do that. And if you're working carefully and you know what you're doing, right, you might kind of say everything here is mod 100, and so we just start working mod 100 in that sense. Well, how does this help us? How does 53 to the 40th power help us? Well, 53 to the 40th power is 1. Well, that means 53 to the 80th power of 1. 53, right, to all of these different powers is 1 in that case. Now, that tells us that 53 to the 1000th, 2000th, 3000th is 1. So in fact, let me just write it off over here. 53 raised to the 3000th power is equivalent to 1 mod 100 as well. And now we'll kind of complete our first box on the top here. Why? Because now if we know 53 to the 300th power is 1, then we actually know that, okay, we just need to calculate 53 to the 5th power mod 100. And this is where the theorem comes into play. We had 3005th power, we can reduce it all the way to just the 5th power, and then we are good from there. Now, there's still a lot of different modular arithmetic tricks you can do from here. So I don't want to spend too much time on these calculations or talking about them, but there's some nice tricks, and a lot of the times you want to still look for shortcuts. So note 53 squared is 2809. Now, this, however, is equivalent to 9 mod 100. Remember, anytime you're doing these calculations, you don't have to actually care about all of the digits in that case. You only need to care about the last two. So even though 53 to the 5th power is a big number, you should never have to deal with any numbers much bigger than thousands or things. Because, for example, then I could rewrite 53 to the 5th power as 53 squared. Well, what's 53 squared? I can write that as 9 squared times 53 mod 100 in that case. And let me just do the work off to the side again here. Now, okay, 9 squared is 81. So what is 81 times 53? So 81 times 53 is 4293. And so, of course, we only, again, care about those last two digits. So the last two digits, or mod 100, are 93 mod 100. And so just to make it clear, on the bottom of this screen, this is telling us that our answer, which is what are the last two digits, the last two digits are just 93 in this case. So we did a lot of this stuff with modular arithmetic. We used Euler's theorem. But in the end, right, the question and answer have nothing to do with those things, right? You can understand this even if you just are learning about exponents. The last two digits, you won't be able to solve the question that way. But I just want to make sure we give our answer as a basic one. It's what are the last two digits, so our final answer should be 93 in that case. Okay. Let's look at another example here and talk a little bit about what can go wrong. So what if we change this problem slightly and we have 35 to the 3005th power? Now, let's write out something right off the bat here. And this is one of the reasons I wanted to write it out before. So what is the GCD of 35 and 100? This is not 1. Right? So this tells us that we cannot use Euler's theorem. We cannot use the extension to Euler's theorem in that case. Now, there are some tricks we can do here. For example, you can do some Chinese remainder theorem things if you want to simplify stuff in that way. But I wanted to do this example as a stress that, remember, we always have the ideas of patterns. We always have the ideas of what happens if you look for a pattern and look for those things there. And the other reason I want to say that is a lot of the times when the GCD is bigger than 1, those patterns tend to be a little bit simplified in this case. So let's write these out here again. So we have 35 to start with. 35 is just 35 in this case. There's nothing to say there. But then what about 35 squared, right? So just to do the pattern in this case, I want to say 35 squared is, of course, 35 times 35 here. And then 35 squared is going to be 1225. But again, what do we care about? We care about the last two digits. So anytime we're doing this calculation, we only have to worry about the last two digits in this case. So we have 35 squared is equivalent to 25. Those are the last two digits for this setup there. Now, what about 35 cubed? So let's do 35 cubed here. And this will be the one that is good practice again with modular arithmetic. Why? Because I want to think about this as 35 times 25. This is equivalent to 35 times 25. Why is that? Because 25 is 35 squared mod 100. So that is where we can not have those big numbers again. This is similar to what we did right at the end of the previous problem. So this is equal to or equivalent to 875. So this has last two digits of 75 mod 100 in this case. Now, I'm going to color code this as a little bit of a hint, but let's do one more line here. So what is 35 to the 4th power in this case? So following the same pattern, this is 35 times 35 cubed. So that is 75. It's equivalent to that mod 100 in this case. So this is equal to 2625. But again, we only care about the last two digits, which are 25 mod 100. Now, why am I color coding these? Why am I stopping here a little bit? Well, notice that 35 squared is going to be 25 mod 100 in this case. So we have that one there. Then that matches the 35 to the 4th power. And, well, what would happen if we did the 5th power? Well, it's going to look identical to the 3rd power, because we're going to have 35 times 3 to the 4th power, but that's also 25. So we see that after the first term, this pattern repeats 25, 75, 25, 75. So our pattern in this case, right, I just want to stress it doesn't have to repeat starting with the first term. So this is something that can happen that we need to be a little bit aware of. It's 35, then 25, 75, and then that 25, 75 is what repeats. So the 35 never comes up again, but every odd term after the first is going to be 75 in this case, meaning that our answer in this scenario, because 3005 is an odd number, is 75. So the last two digits of this power of 35 are 75 at the end. Okay, that will do it for this video. Thanks for watching. If you liked this, please like the video, subscribe to our channel. Check back the last couple of weeks of 2021 for a new math tidbit. Stay tuned for what's in store for 2022. And if you're looking for some more practice and resources, check out ziml.areteem.org. Have a great day, everybody. I'll see you next time. Goodbye.